Hello and welcome to this lesson on Chateliers Principle. In today's lesson, we will understand the concept of Chateliers Principle as it pertains to chemical equilibrium. We will then recognize that when a chemical system at equilibrium is disturbed by changes in pressure, temperature, or concentration, it adjusts to counteract the disturbance and restore equilibrium. Finally, we will understand the impact of catalysts on reversible reactions. So far, we've talked about reversible reactions, and you've been introduced to the concept of dynamic equilibrium, where the forward and reverse reactions occur at the same rate, resulting in constant concentrations of reactants and products. Building on this foundation, today's lesson will enhance our understanding of how chemical systems react to changes in their environment. By mastering Le Chatelier's principle, we can better predict and control the conditions under which reactions occur, which is a crucial aspect of chemistry in both industrial and laboratory settings. In the previous lesson, we used an analogy of an athlete walking on an escalator to explain dynamic equilibrium in chemical reactions. We discussed how, at equilibrium, the concentrations of reactants and products remain constant because the rates of the forward and reverse reactions are equal. However, these concentrations don't have to be the same, just like how the athlete might be at different positions on the escalator, top, middle, or bottom, while still being at equilibrium. But what if the escalator suddenly speeds up? In this case, the athlete has to walk faster to maintain balance. However, despite their best efforts, they will likely end up closer to the bottom than before. This scenario is similar to what happens in a chemical system when we change conditions such as temperature, pressure, or concentration while at equilibrium. This is where Le Chatelier's principle comes into play. It explains that when a system at equilibrium experiences a change, it will shift to counteract that change and re-establish equilibrium. Just like the athlete trying to walk faster to adjust to the escalator's speed, the equilibrium position of a chemical reaction will move in response to changes in external conditions. For example, increase in temperature will cause the equilibrium to shift in a direction that absorbs heat to lower the temperature back down, changing the position of equilibrium accordingly. Let's now look at specific cases applying Le Chatelier's principle to understand how changes in concentration, temperature, and pressure affect the position of equilibrium in a chemical reaction. Let's start with change in concentration. When the concentration of a reactant or product in a reaction at equilibrium is changed, the system will shift to oppose this change. Imagine adding more of substance A in this reaction. Le Chatelier's principle tells us that the system will push the reaction forward to use up this extra A by converting it into more B. This means the equilibrium will shift to the right, favoring the production of B to reduce the excess concentration of A. Conversely, if we remove some of substance B, the equilibrium will shift to the right, producing more B from A to make up for the decrease. To understand this concept better, let's consider a practical example from the Haber process, used for the production of ammonia, NH3. The balanced equation for this reaction is N2 plus 3 H2 forms and is produced by 2 NH3. What happens if we increase the concentration of nitrogen gas? According to Le Chatelier's principle, the system will try to counteract the increase in nitrogen concentration. But how can we decrease the N2 concentration? By using more of it up. Hence, equilibrium will shift to the right. This means the system will consume more nitrogen and hydrogen to produce more ammonia. The result is a higher production of ammonia, as the system strives to restore equilibrium by reducing the disturbance caused by adding more N2. Now, let's consider the production of hydrogen from methane, CH4, and steam, H2O. The balanced equation for this reaction is CH4 plus H2O forms and is produced by 3H2 plus CO. What happens if we remove carbon monoxide gas, CO, from the system? When carbon monoxide is removed, this decreases its concentration in the system. According to Le Chatelier's principle, the system will try to counteract this change by shifting the equilibrium to the right to produce more carbon monoxide. This shift to the right means that more methane, CH4, and steam, H2O, will be used up to generate carbon monoxide, CO, and hydrogen gas, H2. Thus, removing CO shifts the equilibrium to the right to produce more CO to restore its concentration, simultaneously increasing hydrogen production. Now let's move on to changes in temperature. The effect of temperature changes depends on whether the reaction is exothermic, releases heat, or endothermic, absorbs heat. For an exothermic reaction, where heat is released as the products form, raising the temperature adds more heat to the system. The equilibrium will shift to the left, favoring the reverse endothermic direction to absorb this added heat, thus decreasing the production of the exothermic products and favoring the reactants. For that same exothermic reaction, if the temperature is lowered, the equilibrium will shift to the right, favoring the exothermic forward reaction to produce more heat, thus favoring the production of the exothermic products. For an endothermic reaction, where heat is absorbed, the effect of temperature changes is reversed compared to an exothermic reaction. Raising the temperature adds heat to the system. In response, the equilibrium will shift to the right towards the products to absorb this added heat, favoring the forward, endothermic reaction. This means that more products will be formed as the system tries to balance the additional energy. Lowering the temperature removes heat from the system. To compensate for the loss of energy, the equilibrium shifts to the left towards the reactants, favoring the reverse reaction to generate heat. As a result, less product is formed. Consider the production of hydrogen gas from methane and water again. The forward reaction is endothermic. What would happen if the temperature is increased? What would happen if it was decreased? When we increase the temperature of the system, we are adding heat. According to Chateliers Principle, the system will respond by counteracting this change. In this case, by absorbing the added heat. Since the forward reaction is endothermic, it absorbs heat. Therefore, the equilibrium will shift to the right in the endothermic direction. As a result, more hydrogen gas and carbon monoxide are produced at higher temperatures. Conversely, when we decrease the temperature, we are removing heat from the system. In response, the system will try to generate heat to counteract this change. Since the backward reaction is exothermic, it releases heat. Therefore, the equilibrium will shift to the left in the exothermic direction. Consequently, more reactants, methane and water, will be produced, and less hydrogen gas and carbon monoxide will be formed at lower temperatures. Now consider the production of sulfur trioxide, SO3, from sulfur dioxide, SO2, and oxygen, EO2. The balance reaction is 2SO2 plus O2, produces and is produced by 2SO3. The forward reaction is exothermic. What would happen if the temperature is increased? When we increase the temperature, we are adding heat to the system. According to Chateliers Principle, the system will shift in the direction that counteracts this change. Since the forward reaction is exothermic, releases heat, this means that the reverse reaction is endothermic, absorbs heat. Hence, the system will shift toward the reactants, the left side, to absorb the extra heat. As a result, the equilibrium will shift to favor the production of more sulfur dioxide, SO2, and oxygen, O2, reducing the amount of sulfur trioxide, SO3, formed. Now, let's look at changes in pressure. Changes in pressure affect equilibrium only in reactions involving gases, especially when there is a difference in the number of gas molecules on either side of the equation. If the pressure is increased, the system will favor the side of the reaction with fewer gas molecules, as this reduces the overall pressure. If the pressure is decreased, the system will shift toward the side with more gas molecules, as this increases the overall pressure. Consider the Haber process. N2 plus 3 H2 produces and is produced by 2 NH3. Let's apply Le Chatelier's principle to understand what happens when pressure changes in this system. If we increase the pressure in this system, what does Le Chatelier's principle tell us? The system will shift in the direction that minimizes the change. We want to decrease the pressure by decreasing the number of molecules of gas. Hence, the side with fewer moles of gas will be favored. In our equation, the left side has 4 moles of gas, 1 mole of N2 and 3 moles of H2, whereas the right side has 2 moles of gas, 2 moles of NH3. Increasing the pressure will therefore shift the equilibrium to the right, producing more ammonia, NH3. Conversely, if we decrease the pressure in the system, the equilibrium will shift to the side with more moles of gas to counteract this change. In this example, the left side has more moles of gas compared to the right side. Therefore, a decrease in pressure will shift the equilibrium to the left, resulting in more nitrogen, N2, and hydrogen, H2, and less ammonia, NH3. What if both sides have the same number of gas molecules? When a reaction involves the same number of gas molecules on both sides, a change in pressure will have no effect on the position of the equilibrium. This is because there is no imbalance in the number of gas particles to shift towards either side. For example, H2 plus I2 produces and converts to HI. In this reaction, there are 2 moles of gas on both sides, 1 mole of hydrogen and 1 mole of iodine on the left, and 2 moles of hydrogen iodide on the right. Since the total number of gas particles remains the same, changes in pressure won't favor one side over the other. Recall that catalysts are substances that increase the rate of a chemical reaction without being used up. What happens if we catalyze a reversible reaction? Does it shift the equilibrium at all? Perhaps surprisingly, the answer is no. A catalyst does not shift the position of equilibrium. The reasoning is that a catalyst will increase the rates of both the forwards and the backwards reactions, and by the same amount. Essentially, this makes the reaction reach dynamic equilibrium quicker, but the position of the equilibrium remains unchanged. By understanding these fundamental aspects, we can predict how a system will react to changes in concentration, temperature, and pressure. Let's dive into some GCSE level questions to apply our understanding of Le Chatelier's principle. Question 1. Consider the reaction CO plus 2H2 decomposes to form CH3OH methanol, with the reaction being reversible. What happens if the concentration of H2 is increased? Pause here to have a go. Now, let's go through the answer. When the concentration of H2 is increased, the system will respond by trying to reduce the excess H2. According to Le Chatelier's principle, the equilibrium will shift to the right, favoring the formation of more methanol to use up the extra H2. This shift increases the production of methanol and reduces the amounts of CO and H2. Question 2. For the endothermic reaction CaCO3 produces CaO plus CO2, with the reaction being reversible, predict what happens if the temperature is increased. Pause here to have a go. Now, let's go through the answer. Since this reaction is endothermic, it absorbs heat as it proceeds in the forward direction. When the temperature is increased, more heat is added to the system. According to Le Chatelier's principle, the system will shift to the right, favoring the forward reaction to absorb the extra heat. As a result, more CaO and CO2 will be produced. Let's look at one final question. Consider the reaction 2NO2 produces N2O4, with the reaction being reversible. What will happen if the pressure is increased? Pause here to have a go. Now, let's go through the answer. This reaction involves gases, with 2 moles of NO2 on the left side and 1 mole of N2O4 on the right. When the pressure is increased, Le Chatelier's principle states that the system will shift toward the side with fewer moles of gas to reduce the pressure. In this case, the equilibrium will shift to the right, resulting in more N2O4 being produced and less NO2 present. In today's lesson, we delved into Le Chatelier's principle and its application to chemical equilibrium. We learned that a chemical system at equilibrium will adjust to counteract changes in concentration, temperature, or pressure to restore equilibrium. First, we discussed how changes in concentration affect equilibrium. Adding more reactants or removing products shifts the equilibrium to favor product formation, while removing reactants or adding products shifts it towards reactant formation. Next, we examine the impact of temperature changes. For exothermic reactions, increasing temperature shifts equilibrium to favor reactants, while for endothermic reactions, it favors products. Conversely, decreasing temperature has the opposite effect. Next, we explored the effects of pressure changes on gaseous reactions. Increase in pressure shifts equilibrium towards the side with fewer moles of gas, while decrease in pressure favors the side with more moles of gas. Finally, we discussed how catalysts have no effect on the position of equilibrium, as they speed up the forwards and backwards reactions by the same amount. By manipulating these factors, concentration, temperature, and pressure, industrial chemists can control the position of equilibrium to maximize product yield, making these concepts critical in fields like chemical manufacturing. We will see a practical example of this in the next lesson. Watch the rest of the GCSE chemistry course at Sophos Education.